Okay, so throughout my time tutoring, I've gotten asked the question lots of times, what are NPVs? Okay, so when we're simplifying rational expressions or we're solving rational equations, we always have to list the NPVs or else, we lose marks on tests or the question is not fully solved, right? So in this video, I'm going to explain what NPVs actually are, why we need to address them, and how they might look on graphs, how they can change our functions or expressions, okay? So NPVs, let me just write here. NPV stands for non-permissible value. Okay, so it's a value for x or y or whatever a variable is that makes a function undefined. Okay, so what is an undefined function? Well, there's a couple ways a function can be undefined, but the most common way is if the denominator is 0. So let's say we had the number 5, right? And we divided it by 0. This would be undefined. So if our function at any point was considered to be 5 over 0, then the function at that point would be undefined. Okay, so let's say we had a rational expression like x plus 3 over x minus 2. Okay, what are the NPVs, or what's the NPV for this rational expression? Well, NPVs are when the denominator is 0, so we take this whole denominator and we say this cannot equal 0. Okay, so we kind of make an inequality equation out of it. We say x minus 2 cannot equal 0. Okay, and now we can just kind of solve this inequality. We add 2 on both sides, treat it like it's an equal sign, and we say x cannot equal 2. So x equals 2 is a non-permissible value. If x is 2, then this whole thing is undefined because the denominator becomes 0. Okay, what's another example? Let's say we have somewhere in our equation or expression, let's say our expression is x squared plus 5x plus 4 over x squared plus 9x plus 20. Okay, so whenever we get a question like this is a rational expression, right? It's not an equation, but in both cases, we're going to factor the top and bottom and see if we can cancel anything. So let's factor the top first here. So we need two numbers that multiply to 4 and add to 5. So that's going to be x plus 4 times x plus 1, okay? And now the bottom here, x squared plus 9x plus 20. We're going to need two numbers that multiply to 20 and add to 9. So that's going to be x plus 5 and x plus 4. Okay, and now we can just cancel out the top and the bottom, right, like we did in the last video. So we get x plus 1 divided by x plus 5. So you might have remembered when we did questions similar to this that I said this expression right here, this is not exactly equal to this expression right here. It's a simplified version, and we canceled out the x plus 4. Everything was right, except the only difference is that the NPVs are different. Okay, so let's see the non-permissible values for this part right here before we canceled the x plus 4s. Okay, so remember we said it's a non-permissible value if it makes the whole denominator 0. So see how if we put in negative 5 for x here, or negative 4 for x here, this would be like negative 5 plus 5, which would be 0, or negative 4 plus 4, right, which would make this 0. So if x was negative 5 or negative 4, then the function or the expression would be undefined. Okay, so those are our NPVs for this row right here. So x cannot equal negative 5, right, and x cannot equal negative 4. But see, for here, for this part, our only NPV, right, we say the bottom cannot equal 0. So we subtract 5 on both sides, and we say x cannot equal negative 5. So x can't equal negative 5 is our NPV, but see how this x equals negative 4 NPV disappears because we canceled out the x plus 4 on the top and bottom. So it's not the exact same expression, it's just simplified. And if you were to graph the two, you would have different what's called holes in the graph. And I'll show you what a hole in a graph is right here. Okay, so right here I graphed the equation y equals x squared plus 7x plus 10 all over x plus 5. Okay, and you might be thinking, well, why does this look like a line? Because there's an x squared in the top, and I thought x squareds had like a kind of a U-looking parabola shape. And that's true, but remember we have an x squared and we're dividing it by an x, right? So the degree of the function is 1. And if you think about it, we can simplify this, right? So we have x squared plus 7x plus 10. That's over x plus 5. That's the same as, when we factor it, right? That's the same as x plus 5 times x plus 2 over x plus 5. So we see an x plus 5 on the top and bottom, and we're just left with x plus 2. So this line is the same as y equals x plus 2, right? We have a y-intercept of 2, and we have a rise over run of 1. It's 1x plus 2. The only difference is now we have an NPV, x can't equal -5. So if you were to graph this original function, this original kind of relation, it wouldn't be exactly the same as x plus 2 because you can see right here, the graph on Desmos tells me that when x is -5, right, if I go to -5 and I kind of draw a line down, there's going to be a hole in the graph. So that's why they just drew a literal hole right here, because at an NPV, there's going to be a hole in the graph because it makes the function undefined. It doesn't exist there, right? Because when x is -5, our denominator becomes 0. Okay, so if I were to plug this in, right, if I made x -5, this would be -5 squared plus 7x plus 10 over -5 plus 5. And I'm just going to fill this in with -5, right? Sorry for the messiness here. So it's 25 minus 35 plus 10 over 0. And it looks like this is actually going to be 0 as well on the top. So this is just 0 over 0. So, but my point was that even if the top number is positive, so let's say this was like 20 over 0, it's still going to be undefined because our denominator is 0, and that's why there's a hole in the graph right here. So the main idea is that to find your NPVs, you always set the bottom, the denominator equal to 0. Those are going to give you your NPVs, and an NPV on a graph is just going to look like a hole. So let's say your NPV, let's say x could not equal 2. Well, on a graph, if you found x equals 2 and you drew a line straight up to where the line is, you would find a hole right there, right? If you were to graph it on Desmos or something. So I hope that kind of gives you an intuitive understanding to what NPVs are, and in my next video, I'm going to go over how to solve rational equations. See you in my next video.